We have many other materials which are involved in the fabrication of MEMS and many other new processes that have been added to the manufacturing industry. In particular, one of the most important components of the MEMS, which is not found in microelectronics, is silicon. The polydimethyl siloxane structure that I have described, which has in the backbone the silicon and the oxygen atoms, is actually used very much in the microfluidic systems that allow the flow of certain substances, or in the seals of the MEMS when you have microfluidics, so you couple together electrical phenomena and liquid flow. Other very important material is the parylene, which is a thin film with very important electronic properties. It is used and deposited by means of a chemical vapor deposition, meaning that you put the substrate where you want to deposit this material into a controlled atmosphere under controlled thermal profile, and there you will have the deposition of a conformal layer of a polymer starting from vapor phase. Very much important are other inorganic materials like the silicon carbide. We have already talked about this, which has huge thermal resistant properties, so it's very important for particular applications. For example, in the car industry, where you have silicon chips and devices which should stay under the trunk close to the engine, where the temperature, the inner temperature during working is around 80 degrees Celsius, you should use this kind of electronics that well survives the thermal environment. Another important material that is used in the MEMS fabrication but is not found in microelectronics is the piezoelectric material. So surface acoustic waves injectors, health monitoring systems, pressure sensors, all those devices have in common a piezoelectric ceramic material. And the most important engineering material is the PZT, so the lead zirconium titanate, which is toxic. So European regulations will completely hinder the market to this material, and in the future years we will see the development of new greener materials. Also, magnetic materials are very important for the MEMS fabrication. Maybe the most important one is magnetite, so it's iron oxide, iron 2 or 4, iron 3 or 4, which is a very stable material having a good magnetic remanence. Regarding the new processes that are used to fabricate MEMS and that you cannot find easily in the microelectronics, we have laser processes. Lasers which are focused on a substrate may have two effects. First one is the ablation. So if the energy connected to the laser beam is huge, you may evaporate atoms from the material and bring them away directly, so digging huge holes in the material. Another possibility is that of laser sintering. So if you have a particulate system, the laser brings heat and thermal energy to your system and allows you to reach a melting temperature or enhance surface diffusion, so that particulates, systems or grains or particles start to coalesce together. Another important technology is the deep reactive ion etching. Etching techniques mean that you want to remove materials from a certain location, and usually you do this by wet etching, meaning that you use acids or corrosive substances which are in a liquid phase, or plasmas. Plasma is something which is charged from the point of view of electrical field and is conveyed and releases kinetic energy by removing atoms in an ablative fashion. So deep reactive ion etching is something that is able to reach a huge aspect ratio while digging holes into a two-dimensional substrate like a silicon wafer. And higher aspect ratios are very important for the fabrication of MEMS structures. Another very important technology is the focused ion beam. Focused ion beam means that I am treating the ion beam as an electron beam or as a laser. So I'm focusing it and I'm able to provide huge resolution to this beam, meaning that I can raster it, and wherever the beam hits the matter, it generates ablation of material. So it is used to write into the material structures with a very low dimensionality, down to the hundreds of nanometers. Chemical mechanical polishing is normally used to flatten the surface after all the processes, and to obtain something that could realize a tight seal when coupled to a polymer or to a glass. Rapid prototyping is another very important technology used in MEMS, and hopefully also in the NEMS in the future. So it is an additive way of manufacturing, like the 3D printing systems or like the inkjet printing systems. Nanoreplica molding is another interesting approach, which allows to realize easily and with a quite high throw output nanostructured surfaces. So the idea is that I realize with the maximum effort at the highest resolution one single example of my geometry, and then I couple it with a PDMS mold, and the mold it makes a perfect copy of the surface. So when I use this mold as a replica to print certain materials or to transfer certain materials on another matter, then I have easily repeated an unstructured or microstructured geometry on another substrate, and I can repeat this process many times because silicon is quite tough and it's not degrading. Deep pen nanolithography is something even more interesting. It looks like an atomic force microscope, so where the principle is to have a very sharp needle whose radius of curvature in the tip is around certain hundreds of atoms, so it's very, very small. That tip is scanned across the surface in a raster way, and it is possible to move even single atoms on this surface while realizing an electrical connection or a chemical bond between the tip and the atom that you are moving on the surface. So this is actually a real nanofabrication tool where you can build your own structure atom by atom. Of course, it's very slow, and it's very much important to maintain a controlled atmosphere, so without any vibration, without atoms coming from the atmosphere and fixing to the substrate. So everything must be very controlled, and it's not a very fast method, of course. So how is it made, a MEMS or a NEMS? The first phase is to determine the required properties. So having in mind what you want to realize, you end up with a list of requirements. Second phase is to understand what kind of material is suitable for those applications and which responds well to all your requirements. And the third phase is to better design the processing technique that allows you, starting from a certain material, to match the requirements that you have given earlier. Which is the classification of the materials used for MEMS and NEMS regarding the properties? So mechanical properties. Of course, the most important one is stiffness, which is a Young modulus, but elasticity is also known as Young modulus. This means that when I apply a stress, I obtain a strain, and when I remove the stress, also the strain is going back to the initial state. This is elasticity. When the state is not recovered, we have a plasticity, which is even important when you have the necessity to have deformable structures that should not recover ever the strain that they have accumulated. Strength is another important factor, which is the proportionality constant between the stress and the strain. The ultimate strength is the maximum value of stress that you can reach in a structure before breaking it. Brittleness or toughness is the difference between two behaviors regarding the impact of a certain object. Okay, so if the resistance to impact is high, then you have a tough material, otherwise it's brittle. So depending on the application, you may need one or the other. Fatigue is another important thing, where we have seen the importance of the surface smoothness. So the absence of flows on the surface allows you to achieve huge fatigue resistance. What about the thermal properties? Thermal properties normally are connected to the heat dissipation capabilities of the material. It's very important in MEMS and microelectronics too. So certain kind of ceramics, in particular nowadays, aluminum nitride is one of the most studied one. It is an insulator material, but is able to conduct very well heat. So it's used to dissipate and connect all the transistors towards the fins and the heat dissipation systems which are outside of the CPU. The heat capacity is another important factor. So if you want to store heat and release it slowly, you should have a material with a huge heat capacity. One of the most important of them is water, which has a huge heat capacity. Regarding the electrical properties, we may use, of course, conductivity and resistivity, which is the opposite of conductivity. But there are many others details that have to be assessed. In particular, if you are watching the conductivity in the DC state or in alternate frequency currents. Dielectric properties involve capacitance, for example, or other kind of dielectric properties like piezoelectricity, ferroelectricity, or pyroelectricity, which are the ability of generating charges in response to a pressure field or in response to a thermal gradient field. Regarding magnetic properties, we have substances that could add to your MEMS or NEMS structure ferromagnetism, meaning that you are able to store a magnetic dipole, or paramagnetism, meaning that the response of the material is opposite with respect to the applied field, so they repel actually the magnetic field, or diamagnetism, meaning that no magnetic field streamline is able to go through your material. And actually, this property is exploited to realize the so-called diamagnetic levitation. So when you have a very strong permanent magnet and you want an object to fly over this, you should use diamagnetic materials, for example, as bismuth, which is the strongest diamagnetic material known in nature. Another example is given by superconductors. So naturally, superconductors, when are below the transition temperature and are in their superconductive state, repel the magnetic field streamlines and are able to fly over a permanent magnet, which is exploited, for example, in extremely fast maglev, magnetic levitation trains and transportation systems. Some other optical properties, it's important to have, for example, the control over refraction index in order to directly guide the electromagnetic energy through a fiber, for example. Absorption is important, reflection and transmission, of course. If you have a solar panel, the surface of the solar panel should not reflect the light too much, so you should use thin layers of anti-reflective coatings to avoid this. Birefringence could be used. For example, we have seen plasmonic resonance in certain materials, so this is able to absorb a certain wavelength and allow you to have different colors depending on the fact that if the light is observed in transmitted light or in reflected light. Corrosion properties, so the corrosion rate should be tunable depending on the environment. In particular, for example, if you want to realize a material which is able to withstand atomic oxygen while going in the outer space, you should avoid the use of metals because they easily interact with the oxygen. Better to use the ceramics, which are already oxidized. Other materials for harsh environments, you may think of materials which do not deteriorate at huge temperatures. So refractories are very important, for example, as a thermal protection we have seen of the shuttle or of those systems that should re-enter without destroying themselves. Chemical properties are very important when you have to place in contact a material with some substance which is corrosive. For example, you may think of fuel tanks. If you have, for example, hydrazine or nitric acid, which were used as rocket fuels, you should carefully select a material that contains those liquids. Biological properties, of course, are mainly toxicity and biocompatibility. This is the last important concept I want you to tell about, which is the Ashby plot. So the Ashby plot has one very simple principle It was developed by my colleague at the Cambridge University. So the idea is to plot the engineering properties of materials in log scale, both in the x-axis and in the y-axis. In particular, all those plots have on the x-axis the density of the materials, and on the y, the property of interest. In this case, we have a fracture toughness, which is a measurement of the energy that can be dissipated by the material during an impact. So what happens is that you may easily see how different categories of materials compare to each other. The metals, the ceramics, and the polymers, and how the polymers and the composites are important to save mass, in the sense that if you consider the absolute properties, probably without comparing them to the mass and to the density, the metals and the ceramics are the best choice of materials. But the composites and the polymers gain importance when you want to have the highest properties and the lowest density. Those plots help you to design a MEMS or NEMS and to select correctly the category of material that you want to involve in your fabrication process.